Okay, this is about moles, mass, and Avogadro's number. When we use the mass on the periodic table here, the smaller number, I know you can't read it that well, but the smaller number is the atomic number and the bigger number is the mass number. And so with this tutorial, we'll be talking about the mass number. So first thing, we're going to talk a little bit about exponents. When you multiply 10 to a power, you add the exponent. So if we're multiplying 10 to the third times 10 to the fifth, you add 3 plus 5, it would be 10 to the eighth power. So you add the exponents. If you have a 10 to the minus 2 plus 10 to the sixth, again you add the exponents. A minus 2 plus a 6, minus 2 plus a positive 6, when adding a minus and a plus, take the difference between them and give it the sign of the larger. So a minus 2 plus 6 would be a 4. So again, when you multiply with exponents, you add the exponents. 10 to a power. It has to be 10 to a power. And when you divide, and when we do those Avogadro number problems, you'll be dividing numbers. And so 10 to a power, divided by 10 to another power, you subtract top from bottom. So 8 minus 5 is 3. If you have 10 to the eighth, and again, 10 to the eighth would be 10 times 10, 8 times. 6, 7, 8, divided by 10 to the 5. And if you would cancel these out, they would cancel out. Whoops, 1, 2, 3. Whoops, I had too many there. Okay, and we would have 10 to the third power. Okay, we would have 10 to the third power. So you subtract 10 to a power divided by 10 to a power, your top minus bottom. Now this is a tricky part. If you have a minus 2 on top, a minus 2 minus plus 7, when subtracting, you change the bottom number and give it an add. So a minus 2 plus a minus 7 is a minus 9. And that's where a lot of my students have problems. So that top minus bottom, so a minus a negative, okay, a minus a positive, you change the bottom to negative and then add them. So it would be a minus 9. So again, when you divide, you 10 to a power, you subtract the exponents, top minus bottom. So moles are a conversion factor. Okay, moles are we use to convert one thing to another. Just like if we know 1 dozen apples, okay, the word dozen is 12 apples, we can say it as a ratio. Dozen apples is to 12 apples, or 12 apples is to a dozen apples. It's a ratio. 1 hour is to 60 minutes, or 60 minutes is to 1 hour, equal. Okay, they're equal when we set it up as a ratio. Well, moles and grams, the mass and the Avogadro numbers is pretty much ratios. Okay, so just like 12 objects are in a dozen, a mole is a counting. A mole is the amount of substance that contains the same number of particles as the number of atoms in 12 grams of carbon. So that Avogadro's number, there are 6.022 times 10 to the 23rd particles in a mole of a substance, and that's Avogadro's number. 1 mole equals that many particles, just like 1 dozen equals 12 particles. 1 mole equals this many, either could be atoms or molecules or ions. We just say representative particles, depending on what we're talking about. Okay, just kind of think of it as like 1 dozen equal to 12 things. So if we look at the mass of carbon in the periodic table, now let's flip back to that. I think I have a periodic table in here. Okay, if you look here, you can't really see, but if you look at a periodic table, the big number would be about 12 grams. Okay, the big number would be 12 grams. So we have 12 grams of carbon contains this many atoms, and that equals 1 mole. Okay, so 1 mole of carbon, and we use this as a kind of a, just shorthand. 1 mole of carbon is 12 grams. I got that off the periodic table. That's the mass of carbon, and that equals 6.02 times 10 to the 23rd particles. So if I would weigh 12 grams of carbon on a scale and count the particles, I would get this many particles, 6.022 times 10 to the 23rd actually atoms. In this case, carbon, we would be talking about atoms. If I look at helium, the mass of helium is 4 grams. 1 mole of helium would be equal to 4 grams, and if I would count all the particles, the atoms, in 4 grams of helium, I would get this number, Avogadro's number. And that would be, in this case, atoms, because I was just dealing with one element, helium. Here I'm just dealing with carbon. So 1 mole of a substance contains this many particles. Think of it this way. A dozen M&Ms, if 1 M&M is a gram, a dozen M&Ms would be 12 grams. A dozen pencils, if 1 pencil is 5 grams, a dozen pencil is 60 grams. And a dozen eggs, let's say 1 egg was 20 grams, so a dozen eggs would be 240 grams. So you can have a dozen of different things, and they'd be different masses. Okay, different masses, just like a mole of carbon has a different mass than a mole of helium, which has a different mass, let's say, than a mole of water. Okay, and just think of a dozen, compare M&Ms to pencil to eggs to whatever. 1 mole, a dozen would have different masses if you would just weigh a dozen of each of those things. So 1 mole of an atom equals, if you look at the mass in the periodic table of whatever you're talking about, and that equals that many particles. It can change. These would be atoms. This would be molecules. Here we have, this would be ions. This is a molecule. It's more than 1 element. Here we have 2 elements bonded together, so that's a molecule. Here we just have 1 thing. That's an atom. So the name of the representative particles changes depending on what we're talking about. Okay, so molar mass. Now moving on to a molar mass of an element or a compound. Molar mass is the mass in grams of 1 mole of a pure substance. So I had used that example. 1 mole of carbon is 12 grams. If I would put 12 grams of carbon and count each atom, I would have this many atoms. That's Avogadro's number. Magnesium, if I look in the periodic table for the mass, you see the 2 numbers, the little number and big number. The little number is the atomic number. The big number would be the mass number. So if I look up magnesium on the periodic table, I would see the mass is 24.3 grams. So 1 mole, if I would put 24.3 grams of magnesium, and then if I would count all the atoms, I would have this many atoms. Now water. Water has 2 oxygens and 1 hydrogen. 2 hydrogens and 1 oxygen. So if I look up on the periodic table to get the molar mass of water, I'd look on the periodic table the mass of hydrogen. Mass of hydrogen is 1 gram, but I have 2 of them. So I'd have 2 grams of hydrogen. I look up the mass of oxygen on the periodic table. It's 16 rounded. It's like 15.99. I would round it to 16 grams, and then I would add that up. 16 plus 2 is 18 grams. So 1 mole of water would be 18 grams. I add up the molar mass of each of these, whatever we have. And this number goes with the number, the element in front of it. So it would be 2 hydrogens, or 1 is understood here, 1 oxygen. So if I would weigh 18 grams of water and then count the molecules, here notice this atoms because I just have carbon and magnesium, but if I would count the molecules of water, I would have this many molecules of water in 1 mole of water. So 1 mole of, and so we would use these conversions 1 mole of water equals 18 grams equals this. And I would use that as conversion factors when converting, let's say, moles to grams or moles to molecules. Let's look at sodium chloride. Again, I look on the periodic table. The mass of sodium is 23 grams. Mass of chlorine is 35.5. I add them up. So 1 mole of sodium chloride is 58.5 grams. And if I would weigh that, I didn't write it on here, but if I would weigh that, it'd be 6.02 times 10 to the 23rd molecules. So we would use these equivalents as conversion factors, just like we would use 1 hour equals 60 minutes, 1 minute equals 60 seconds to convert between hours and minutes or minutes to seconds. Here I have this little road map. Here we have moles, and this kind of maps out how to convert. If I'm given mass, if somebody says we have so many grams of something, and how many moles do we have, I would use a conversion, 1 mole over the molar mass, and I'll show examples. Here is representative particles. If I was given, so many atoms of something, and I want to know how many moles, I would use this conversion factor. If I'm given moles and I want representative particles, I would use this conversion factor. Let's clear the page. Let's go to an example.